Okay, this is part 2 of your KIN 425 lecture for Wednesday, February 10th. So I'm going to pick up where I left off on this question sheet. So we were on this question, how would the structure of the heart differ for a strength-trained athlete compared to an endurance-trained athlete, and then compared to someone with extreme hypertension. So there's different stresses that are placed on the heart in each of these situations. So in the case of a strength-trained athlete, they're chronically experiencing acute sessions of high blood pressure each time they do a weightlifting exercise. So when you lift a weight, your blood pressure goes up quite a bit. And then when you're doing endurance exercise, the difference is that your blood pressure goes up a bit, but there's mainly a stress on the heart where you get a large amount of blood returning to the heart. So in the case of the strength training exercise, it's called a pressure overload, and that causes a thickening of the walls of your ventricles. So here you have an ultrasound of the heart. You have your left ventricle, your right ventricle. So with a strength-trained athlete or someone with chronic hypertension, you see a thickening of the ventricular walls. The difference between the strength-trained athlete and the person with chronic hypertension is the strength-trained athlete, it doesn't appear to negatively affect their heart function. Whereas with someone with hypertension that's chronic, over time they would have reduced heart function. So that's called a pressure overload. With an endurance-trained athlete, they get an increase in the volume of the ventricles. So they'll get an expansion of the left ventricle, an increase in the diameter of the left ventricle, or an increase in the volume. So again, in the endurance athlete, it's called a volume overload, and that tends to enhance the heart function over time. And in the strength-trained athlete, it's called a pressure overload. And when you get changes in the cardiac structure, you see changes at the cellular level. So I'm going to quickly go over to the whiteboard here. With your heart tissue, just like in the muscle tissue, you have sarcomeres. So I'm just going to draw actin and myosin here. So this is two sarcomeres. This is your actin in this picture, and this is your myosin with its heads. So it's just like skeletal muscle. In your cardiac muscle, you actually have these contractile proteins, actin and myosin, that form cross bridges with each other. So with endurance training, the change you'll get is, this is endurance training, you get what's called an eccentric overload, or eccentric hypertrophy. And this is from that volume overload. So eccentric hypertrophy, what happens with the sarcomeres is you're going to get an increase in sarcomeres, but they're going to be increased end to end. So you're going to get something like this instead. So you're getting an increase in the number of sarcomeres, but they're increasing in series. So that's the term in series. So eccentric hypertrophy caused by volume overload, and the sarcomeres are said to increase in series. With strength training, on the other hand, what you get is that pressure overload, and you get what's called a concentric hypertrophy. where the sarcomeres will increase, but they'll increase in parallel is what it's called. So they actually get stacked on top of each other. So they're increasing in thickness. So there's your actin and your myosin. So this is an increase in parallel. So endurance training, volume overload, eccentric hypertrophy, the sarcomeres are increasing in series. With strength training, you get a pressure overload. Concentric hypertrophy, you get an increase of the sarcomeres in parallel. That results in a thickening of the walls of the ventricle in the case of a strength trained person, and you get an increase in the volume of the left ventricle and probably the right ventricle as well in an endurance trained person. With the strength trained person, you get really no change in cardiac function. With someone with hypertension, they'll get a thickening of those walls and they get a decrease in cardiac function. With the endurance trained person, you get the increase in the volume of the ventricles and you get an enhancement of cardiac function. So I go back to the problems here. Indicate which of the following variables, how the following variables would change, increase, decrease, or stay the same during rest, submaximal exercise, and maximal exercise following chronic endurance training, so several months. So you're assuming that the submaximal exercise is at the exact same intensity as before training, but the maximal exercise intensity is greater after training. So you're trained, so you're able to go to a higher exercise intensity. So this is the answer. So I filled in all these for you. So your heart rate would decrease at rest and decrease at submaximal exercise. So this is a trained person. After training, their heart rate decreases. And it's about the same at maximal exercise. The heart rate is decreasing because the stroke volume is increasing. The heart's becoming stronger, so the stroke volume increases right across all the exercise intensities. So the cardiac output pretty much stays the same at rest and submaximal because the increase in the stroke volume cancels out the decrease in the heart rate. So the cardiac output is your heart rate multiplied by your stroke volume. So again, you have heart rate multiplied by your stroke volume here, so the cardiac output is the same. But at maximal exercise intensity, your cardiac output is increased. Remember, you're at a higher exercise intensity when you're trained, and that increase in the maximal cardiac output is mainly due to the increase in maximal stroke volume. Now, oxygen consumption is going to be equal to your cardiac output multiplied by your AVO2 difference. So your cardiac output your oxygen consumption increases at maximal exercise, whereas it stays the same at rest. At submaximal exercise, it probably stays the same, but it might decrease if the person is becoming more efficient at the exercise. So often you'll see a trained individual, they will become more efficient, for example, at running or cycling, and that results in a decreased energy expenditure for a given workload. So sometimes you see a decrease in oxygen consumption at the same level of submaximal exercise. You can see your AVO2 difference. This is your oxygen extraction at your tissues. It stays the same, but it increases at maximal exercise. So you become better at extracting oxygen at a greater exercise intensity. This is mainly because you're going to a greater exercise intensity. Coronary blood flow. This represents. This can also represent myocardial oxygen consumption. So coronary blood flow largely determines your coronary oxygen consumption. So there's a decrease at rest and submaximal exercise because the heart is not working as hard, so it demands less of a blood flow. And then at maximal exercise, it's either the same or it might increase because you are working at a higher intensity in a trained state at maximal exercise. Blood flow to the kidneys and livers. This is important for gluconeogenesis during exercise. So it's the same at rest. It increases during submaximal exercise. So you can remove lactate better this way and get increased gluconeogenesis. Then at maximal exercise, it's about the same. Blood flow to active skeletal muscle, you can see it increases during exercise. Blood flow to the skin is going to be the same across, but sometimes it increases if you're training in a hot environment. So blood flow to the skin is important for cooling the body, and you become better at cooling the body in a hot environment if you train in a hot environment. So that's why I have increase there. And then your blood lactate levels, because your muscles are becoming more aerobically trained and you get a greater blood flow to the liver, which removes lactate, you get a decrease in lactate at the same submaximal exercise intensity following training. It's the same or increases at maximal exercise because you go into a higher intensity in the trained state.